In this video, we will study simple harmonic motion. In this video, we will study simple harmonic motion. Simple harmonic motion. So simple harmonic motion is a type of motion which is generally defined as, in simple harmonic motion, the force acting on the object is proportional to, the force is proportional to the displacement, and it's in the opposite direction of the motion. So let's consider an example. Let's say we have a mass. We have a mass which is connected to a spring. The mass has some amount of mass m, which is connected to a spring which has a spring constant k. And let's say we move this mass by an amount x. If you do that, we'll know from experience that if you pull the mass towards the right, the mass will feel a force towards the left because of the spring. So the direction of the force is in the opposite direction, of the displacement, and it is proportional to the amount of displacement you give to the mass. So the motion that results because of this kind of a force is called simple harmonic motion, and we are going to study what are the consequences of this motion. So the force is proportional to the displacement, and the net force in this case is equal to the mass times the net force is equal to the spring constant times the displacement, where k is the spring constant of the spring and x is the displacement. Now, by Newton's second law, we know that the force acting on an object is equal to mass times its acceleration, which is also equal to mass times the second derivative of position with respect to time. So if you use Newton's second law in this equation, which is the simple harmonic motion equation or the spring equation, then we get mass times d2x over dt2 equals minus of kx. Okay? So the second derivative of the position or the displacement with respect to time is equal to negative of the displacement up to some constant which is equal to k over m, which is the spring constant divided by the mass. So let's rewrite this equation as d2x over dt2 equals minus k over m x, and this is generally written as minus omega square x, where omega square is equal to k over m. And omega square is called the angular frequency. Angular frequency. ENCY. Okay. So omega square is called the angular frequency of the motion. And the equation, this is a second order differential equation. So second derivative of x with respect to time is equal to minus omega squared x. This is a second order differential equation. The solution of this equation, we can discuss how to get the solution, but the solution of this equation is of the form x of t is equal to a cosine omega t plus some phase constant. Okay, this is the general solution of a second order differential equation. What this means is that if you take an object like a mass which is connected to a spring, and if you pull it, um, the if you release this mass will now, the position of the mass with respect to time will follow an equation that looks like this. And if you know from your trigonometry, sinusoidal equations, um, this is a sinusoidal function, cosine of omega t. So as time changes, the position would change as a cosine of this function. So it would change sinusoidally with respect to time. So if this was time and this was position, then if you start from this extended position where, remember, our mass system is like this. Initially, if it is at 0, you pull it by some distance x0. So the displacement is equal to x0, which is what I'm going to denote here. Then as you release this mass, it will follow an oscillatory motion, which will be a cosine function, which would look something like this. Okay. The frequency of oscillation, so the frequency of oscillation is omega. So this, let me put it to you this way. So by the time the object returns to its original position, this time would be 2 pi over omega. Okay? And the phase in this case would be equal to 0. And we can discuss all this in a little bit. So this is the general solution. X of t equals a cos omega t plus phi. Now we have to determine what is these constants. A, sorry, how do we go back? We have to, so this is the general solution of your second order differential equation, which we wrote here. And it has two unknown constants, the A and phi. A is the amplitude, phi is the phase. And typically we can find out what is the value of A and phi based on the initial condition. So the initial conditions in this case was we pulled this mass to a certain distance x0 and then we released it. When we released, we didn't push it or we didn't provide any velocity. We just pulled it and released. So by using these two information, we can find out the value of A and phi, capital A and phi. So initially, at time t equal to 0, this is what we did. At t equal to 0, we pulled the mass and released it from the distance x0. So x at time t equal to 0 was equal to x0, and the velocity or the speed of this object at time t equal to 0 was equal to 0. Okay, we did not provide any additional velocity to the object. So now using these two information, we can find out the value of these two constants. So first of all, we know that at t equal to 0, the position was equal to x naught. Okay, so let's use that information. So that says that x of 0, if we use in this formula, x of t equals a cos omega t plus phi. So x of 0 should be equal to a cos omega times 0, because t equal to 0, would be 0, so you will have a cos phi. Okay, and then using the information, the initial condition that x of 0 equal to 0, we can write this as x naught equals a cos phi. Okay, so that's the first piece of information we have used from here. The second piece of information is the velocity at time t equal to 0 equal to 0. So if we have the position x of t, which is a cos omega t plus phi, we can find out what would be the velocity. So velocity, as you know, is defined as the rate of change of position with respect to time, right? And we know that x of t is a cosine of omega t plus phi. Okay, that we know from our solution of the second order differential equation. So now what we can do is we can use the derivative formulas to get what is the velocity. So the derivative a is a constant in this case, so when we apply the derivative we can just take a out, and we will have time derivative of cos omega t plus phi. So what is the derivative of cos of a function? The derivative of a cos of a function is minus sine of that function. So we'll get minus of sine omega t plus phi. So we have taken the time derivative of cos omega t plus phi, which gives me a minus sine omega t plus phi. But the derivative is with respect to t, not with respect to the argument of this function here. So we need to take the derivative of whatever the argument of this cosine function is, which would be d by dt of omega t plus phi, okay, which would give us minus a, the d by dt of omega t would be omega plus phi, and phi is independent of time, so this will give you 0. So you will get minus of a omega sine omega t plus phi. So that is the velocity. Now we know that at time t equal to 0, the velocity is equal to 0, which means that if we apply that to this velocity formula, where velocity v at the time t equal to minus a omega sine omega t plus phi, we will get 0 at time t equal to 0. We know that the velocity equal to 0. We'll get at time t equals to 0, the velocity is equal to 0. So v of 0 is equal to 0. But according to the v of t formula, it should be equal to minus a omega sine omega t is equal to 0. So sine of phi, so minus of a omega sine of phi should be equal to 0. Okay, that is the condition at time t equal to 0. Now, let's think about it this way. Now essentially we have a omega sine of phi is equal to 0. Now let's think about it. A is a constant which we do not know about. Omega we know. Omega would be equal to square root of k and m. So if the mass is not 0 and the spring constant is not 0, this quantity cannot be equal to 0. Okay? So in order for this product a omega sine phi equal to 0, we need either a to be 0 or sine phi equal to be 0. So now what would happen if a was equal to 0? If a was equal to 0, um, let's say a is equal to 0. So a equals 0 and sine phi a equal to 0 and sine phi is not 0. Sine phi is not equal to 0. Well, in that case, here, if a equal to 0, then in here, in x0 equals a cosine phi, whatever value of phi is, x naught would come out to be 0. But x naught is the distance that we pulled the mass by, and if we have pulled the mass by some distance, whatever that distance is, this would be inconsistent with the equation here. So we can definitely say that this is not correct. As long as we have pulled the mass by some distance, this cannot be true. So the only option which is remaining is that sine of phi must be equal to 0. Okay, which implies that the phi or the phase in this case equal to 0, because sine of 0 is 0. Sine of phi would be equal to 0 only if the argument itself is equal to 0 or a multiple of 2 pi, but in this case we will take the condition that phi is equal to 0. So what do we know? We know that phi is equal to 0 now. So we have found out one of the constants, which is phi should be equal to 0, and the second constant we can now find by applying phi equal to 0 in this equation over here, which says that x naught equal to a cos phi. So if phi equal to 0, then when we put cosine of 0, which is equal to 1, which means that x naught should be equal to a. So using phi equal to 0 in the equation x0 equal to a cosine phi, we get a equals x0. Okay, so now we have found out both the constants which were unknown in this equation. So x of t was a cos omega t plus phi. Now we know the values of both these unknown constants a and phi, where a is equal to x naught, which is the maximum displacement that we provided to the mass, and phi is equal to 0. So the initial phase was equal to 0. So let's write down the final equation now. X of t equals x naught cosine of omega t, where omega square is equal to k over m. Okay, this is our solution of the simple harmonic oscillator. Okay, and we can simply say, like, what would be the condition where the if we take the oscillator, we pull the oscillator by some amount x0 from the equilibrium position, and we release, the oscillator will perform its simple harmonic motion. The motion would look something like this. If this is equal to t, it will start initially from the maximum position, which would be x0. Then it will go down, cross the equilibrium position, which is 0 here. Then it will go in the opposite direction, go all the way to some value. Now, what would be that maximum value? We can see from this equation here that the maximum value that cosine of omega t takes is 1, and the minimum value is -1. So the farthest distance it will go in the opposite direction would be equal to minus of x0. Okay, and then it will go back up, cross 0, and then go back to the original position, which would be x naught. Okay, the time it takes to go from its initial position x0 to the position in the opposite direction minus x0 back to the initial position. This is called the time period. Now we can find out what this time period is going to be. So we know that cosine of omega t, to go from x0 all the way back to x0 crossing minus x0 and the equilibrium point twice, to do that, uh, cos of omega t has to be equal to 1, right? Now, what are the values for which cos of omega t is equal to 1? So, cos of omega t is equal to 1. For that to happen, omega t must be equal to either 0 or 2 pi or 4 pi or 6 pi and so on. So essentially omega t has to be equal to 2n pi, where n is equal to either 0, 1, 2, so on. For these values of omega t, cos of omega t would be equal to 1. So the time the object takes to go from the initial position x0 back to the initial position after completing one cycle of going from the initial position to the equilibrium position to the position in the opposite direction and coming back would be equal to would be such that omega t should be equal to 2 pi, right? This omega t should be equal to 2 pi in order for the object to start from this position and come back to the original position. And this time has a special name. It's called the time period, and it is given by t equals 2 pi by omega. Okay, that is called the time period. It's the time which is required for an object in a simple harmonic motion to go from one extreme to the other extreme and come back. In fact, this time period doesn't have to be defined at the extremes. For example, if you have this simple harmonic oscillator, uh, you can take any two identical points. So you can take this point, and the identical point to this would be the point here. Okay, because at this point the object is going from x0 towards minus x0, right? It's going from x0 towards minus x0. Similarly, here it's also going from x0 towards minus x0. So it was at the extreme position x0 and it was going towards minus x0. The point here is not an equivalent point because here the object is going from minus x0 towards positive x0. Okay, so this is not an equivalent point. The equivalent point is here. Okay, and again the time taken from the object to go from one identical point to the next identical point is also called the time period. So it's defined in more general terms. You don't have to take the extreme positions. You can take any two positions in the motion, and the time taken to go from one position and coming back to the same position with the same velocity, same directions, is called the time period. It is defined as t equals 2 pi by omega. Now let's see what is something interesting about this time period. This time period is 2 pi over omega. Now we know that omega equals, or omega square equals k over m, right? So omega would be equal to square root of k over m, which means that the time period is equal to 2 pi square root of m over k, right? That is the time period. Okay, so the interesting point about the time period is this time period depends on the mass of the object, it depends on the spring constant, but it does not depend on how far you have plugged. So it does not depend on x0 or the phase or any other property. So if you take this spring mass system, whether you pull it by 1 meter or 5 meter or 1 centimeter, the time period would remain the same as long as other properties of the system remain constant. So as long as the spring is an ideal spring, the mass is an ideal mass, in that case the time period is independent of how far you pull the mass. Okay, it only depends on the mass of the spring, mass of the object, and the spring constant, not on the extension or the phase or other property. So this is a very interesting property of the simple harmonic motion. Now we can also find out, once we know that the position is x0 cos omega t, we can also find out the velocity and the acceleration. The velocity, if you remember, velocity is defined as d by dt of x of t, which would be d by dt of x0 cos omega t. Okay, now if you take the time derivative here, you will get minus of x0 sine omega t, omega. Okay, minus omega x0 sine omega t. That is the velocity. And then the acceleration, we can also find the acceleration. Acceleration is defined as d by dt of the velocity or the second derivative of the position, the same thing. So if we do the time derivative of the velocity, we would get the acceleration would be equal to minus of omega square x0 cos omega t. So the omega comes because once we do this the time derivative of sine omega t, you will get a cos omega t, and then the time derivative of omega t will give you an extra omega. So you will get minus of omega square x0 cos of omega t. That's the acceleration. Now, so let's look at some interesting properties now. We can plot the position, the velocity, and the acceleration. Let's try to plot them at the same time. So this would be our time. I'm going to plot the position here, x of t, the velocity here, and the acceleration here. Okay, so the position was, if you can remember, the position is x0 cos omega t. It goes as cos of omega t. So at time t equal to 0, the position is the maximum value, which would be equal to x0, and then as time increases, the position first goes down to 0 and then becomes minus of x0 and then goes up again. This is the graph of x of t. Now what would the velocity look like? So velocity in our case, v of t is equal to minus omega x0 sine of omega t. So at t equal to 0, you can see at t equal to 0, sine of omega t would be sine of 0, which would result at the velocity being equal to 0. So at t equal to 0, if you look at the velocity would be equal to 0. So the position at t equal to 0 was maximum. In that case, the velocity is equal to 0. Now, when would the velocity, what would be the direction of the velocity, by the way? So the velocity would actually be negative. So uh, the velocity would be increasing in its magnitude because as omega t increases, the as t increases, omega t would increase and sine of omega t will increase. But so the value of the velocity would be increasing in magnitude, but it has a negative sign here, which means that the velocity is going to be increasing and becoming increasing in magnitude, but decreasing if you look at the direction. What does that mean? Let me try to explain it. So when you pull this object here, okay, let me try to change the color. When you pull this object to this position, remember that we are taking x positive direction towards the right side and negative towards the left side. So when you release this object, the object starts moving in the minus x direction. Okay, and because it starts moving in minus x direction, its velocity is in the minus x direction. That's why at t equal to 0, the velocity would become a non-zero quantity, but it would actually be negative. So initially the velocity will go down, okay, and it will reach its maximum negative value, which would be minus of omega x0 when sine of omega t is equal to 1. Now when is sine of omega t is equal to 1? Sine of omega t is equal to 1 when omega t is equal to pi over 2. Okay, so at this position, when omega t is equal to pi over 2 or t is equal to pi over 2 omega, at this point, velocity will reach its maximum negative value, which would be equal to minus of omega x0, and then it will start reducing in its magnitude and go to zero velocity again when the object is at the extreme negative position. So when it reaches when the particle is at its extreme negative position, minus x0, at that time the velocity will go to 0. And then as the object now from the negative value starts moving towards its positive value, then the velocity will become positive and start increasing. It will reach its maximum value again at the equilibrium point when it is right at the center. When the object reaches right at the center at the equilibrium position, then the velocity will be maximum, and then it will start decreasing again as the object moves towards the extreme. Okay. So let me draw it a little bit more carefully. So whenever the object is at the extreme position, that's when the velocity is 0. And when the object is in the equilibrium position, then the velocity is maximum, either in the positive direction or in the negative direction. Okay, so this would be a cosine of omega t function, this would be a sine of omega t function. Now let's look at the acceleration. Acceleration also follows the same functional formula as the position. So position was x0 cos omega t. Um, acceleration has a similar value. It is minus of x0 cos omega t. But it has this minus sign and an omega squared. So the maximum value of the acceleration gets multiplied by omega squared, the angular frequency squared, and it is in the opposite direction of the position, which makes sense because if you look at our very first equation said that the acceleration is negative of the position, right? It's always negative of the position, which is what we see here. So it's good that our initial formula is satisfied. So acceleration is negative of the position and it's multiplied by omega square. So acceleration would look exactly like our the acceleration would look exactly like our position. Let me draw it here. But it will be flipped. So when the position is x0, the acceleration would be minus of omega square x0, and then when the acceleration, so it will look like this. Okay, so the acceleration a of t acceleration looks exactly flipped as compared to the position. So these are the graphs of the position, velocity, and acceleration. Okay, the velocity graph, there's some error in this. Let me correct this. Okay. Okay, that's good. So these are the positions, velocity, and the acceleration, graph of the position, velocity, and acceleration. Um, any other important quantity? So let me just summarize what we have learned today. Summary. The first we defined what is simple harmonic motion. So simple harmonic motion is a type of motion where the force is proportional to the negative of the displacement. And if we have a spring mass system, which is what we studied, for a spring mass system where the spring has a spring constant of k, the force would be equal to minus of kx. Then we wrote down the equation of motion, which would be mass times the acceleration is equal to minus k over x using Newton's second law. This gave us the equation t2x over dt2 equals minus of omega square x, where omega square was equal to k over m. This was called the angular frequency, We solved this equation to find x of t, which was equal to x0 cos of omega t. From this equation, we found that the velocity was equal to minus of x naught omega sine of omega t, and the acceleration was equal to minus of omega square x naught cos of omega t. This acceleration can also be written as minus of omega square x of t. Okay, then we plotted the graph of x of t, v of t, and a of t, and then we also found out that the time period was equal to 2 pi over omega, which was equal to 2 pi square root of m over k. So these are the things that we learned today. Okay.